My name is Foster Brereton. I'm a senior computer scientist at Adobe Systems, and joining me today is my colleague Lee Thomason, who's a principal architect also at Adobe. Today we're going to be talking about ODR violations and finding them with a tool that we've written called ORC. So we'll go ahead and get started. All right, so the first thing that we need to talk about is the problem. So the issue that we are addressing this afternoon is the one definition rule. The one definition rule in the C++ standard, to give it kind of a layman's definition, obviously there's going to be much more detail in the standard itself. But the layman's definition is that the C++ standard requires that every symbol in your program, every function, every class, all the things that go into defining your program must be defined once and only once. There are, of course, exceptions that are granted to that above rule. For example, when you're declaring a template. However, given that exception, that multiple definition must be generated from identical token sequences. So it basically means the same source file or the same version of the same source file needs to be used in order to generate multiple variations of that same symbol in your program. Now, the problem here is that the standard does not require tooling to detect or report violations of the one definition rule. They do perform some checks along these lines, but they actually, it's by no means is it a comprehensive check to see if the source code that you are building and the final application that you're linking together is in fact clean of violations of the one definition rule. And linkers will actually go so far as to assume that all the inputs into the program that you are building are free of ODR violations. And I'll show you an example of this in a little bit in Xcode. And the standard itself says that if you have even just one violation of the one definition rule in your program, the entire program's behavior is undefined. And at Adobe, our experience with the one definition rule violations is the real world behaviors can range from very benign, seemingly harmless issues to stuff that can be very malignant, very hard to debug, in-field crashes that can just take forever to try to figure out exactly what's going on. Unfortunately, the reality with today's tooling is that there's really no straightforward analysis to look at a single ODR violation and determine if it's going to be, where on the scale of danger it's going to find itself on. So there's no way to know if this is going to be a problem or not until you actually find yourself running code where you hit this particular violation. So this example that I'm giving you here is a bit of a modified example from one that we actually found in the source code of Photoshop. So if you can see this class, we have a class person. The question that I would pose to you is, well, what is the size of this structure? The problem is that depending on how you define the feature there, right in the middle of that data structure, it could either be 48 bytes in size, or if the feature is enabled, it's going to be 72 bytes in size. So the problem is that unless the middle names feature is not, if the middle names feature is not defined consistently everywhere, you have introduced an ODR violation into your code. And so this can exist between one or more components of your code. This can exist between mismatched build variants of your code. It's very easy for something like this to slip in and cause all kind of havoc to get wreaked across an entire code base. And then, of course, everywhere that the person class is being used as a member variable, as a parameter into a function, that's going to cause the size of that parameter to be variable in size. And that is also another place where you can have this ODR violation happen. So once you have a poisoned entity, once you have a poisoned symbol in your source code, that can permeate out through the rest of your source code in very dangerous and unpredictable ways. So the real world examples of ODR violations that we have hit in Adobe, for example, like the previous slide demonstrated, you can have multiple conflicting definitions of the same symbol in more than one compilation unit. So if you have a particular feature that is enabled in some circumstances, but not in others, you can find that inadvertently enabled or disabled in various bits of source file across your application. And then when those are brought together, that's an ODR violation. We actually, through the course of writing ORC, managed to find two completely unrelated definitions of a particular symbol that was logging information out to disk that was 4 namespaces deep, but was a completely different definition. So two people had written 2 completely different logging data structures completely on their own, and yet they ended up using the same symbol name in order to build that into the application. So that was quite an astonishing discovery that we made. You can compile a given header or source file with different compiler settings or pound defines that can cause ODR violations. So for example, if you're building as debug versus release, if you have one source file where you've enabled runtime type identification or another one where you have it disabled, mismatched processor values, if you have a static binary that's being given to you that was compiled with a different version of C++, and then you link it into your application building with a more modern variant of C++. Those are the kinds of issues or scenarios where you're going to be hitting ODR violations. We had another case in Adobe where a component was being delivered to Photoshop and the component had actually overridden operator new and delete, but just for their DLL that they were delivering, and they decided not to export new and delete out of that DLL. So it was not visible. Those custom implementations of those operator new and delete were not visible outside of that DLL. They were hiding it from the rest of the application. But then somebody was taking a standard string as an argument into an API in that DLL. And then when that DLL went to destruct that standard string, it used the bespoke delete operator when the operator knew that was used was the standard provided, the runtime provided operator new. And so you had conflicting implementations of operator new and delete. And that was causing a very obscure crash where it was like, hey, I'm sending this standard string into this API, and all of a sudden, my program explodes and I can't figure out what's going on. And then finally, this is a very common scenario where we have multiple varying copies of a dependency, multiple versions of Boost, multiple JPEG or zlib libraries that have slight differentiations or large differentiations between them. And then bringing all of those together can cause all kinds of problems. So it's also important to understand that one definition rule violations can be embedded anywhere. So simply not using DLLs is insufficient. These can happen when building out a DLL or building out a static library, or even in an executable that doesn't use any kind of DLLs or static libraries to begin with. And I'll give an example of that in a little bit here. So the kinds of behaviors that you can see in your program when we hit a one definition rule violation can vary. They are very subtle. They can be dangerous and they can be difficult to debug. So one of the big issues that we find is obscure, hard to reproduce crashes inside of your code base. And you can even take some time investigating this particular crash and know that it's around this particular set of sources. So you'll isolate those sources in a sample file or an example program. And sure enough, the crash doesn't reproduce there, and you can't figure out why it's crashing over here in my larger binary, but not crashing in my smaller, more discrete sample application. We can also see a lot of erratic debugging behaviors. So you can find yourself wanting to jump into routine X only to find yourself in routine Y and having no idea how you got there. Oftentimes in the debugger, you can try to evaluate values and look at the various member variables that exist or member fields that exist in a data structure. And the values look corrupted, even though, just the line before you properly constructed that data structure. And so you're having a disconnect there between what you expect to see in that data structure and what the debugger is reporting to you. So you get that general sense like the debugger is lying to me here, and I don't understand why. And the code reads properly, Most of the time, that's because you have encountered a one definition rule violation, and you're seeing a conflict between what the debugger understands to be the binary layout of a data structure versus the actual layout of that data structure in runtime. Another example that we find is exceptions failing to get caught. So somebody will try to throw an exception and catch it just a couple lines down, and it will blow right through that catch clause and up higher into the application, possibly terminating the application, and they won't understand why. And then, of course, mentioning the example that I gave in the previous slide, you can crash in the destructor of a C++ data structure after you've passed that object across the DLL boundary. We had one computer scientist inside of Adobe who was actually flown up to a remote location in order to help figure out exactly what was going on in a production build of an Adobe product, and it ended up being this particular DLL boundary issue that we hit in production. So it's
expensive computer scientist.
Yes, very expensive computer scientist. Yes, so it was definitely not a fun one to have to pay for, but we're hitting them all the time. All right, so the solution that we've provided is ORC, and I'm going to go ahead and give a demonstration of this now. So let me go ahead and share my screen into Xcode. So here I am inside of Xcode, and you can see I have 3 source files up. On the left-hand side, I have the definition of an object data structure, and you'll see that I have 2 virtual routines inside of this object data structure. So this is generating a vtable, and there are 2 possible entries that exist inside of this vtable. However, one of them will only be defined if that enablement flag macro in line 13 is actually defined. When it's not defined, the only entry in my vtable is going to be this API routine down here. So then the 2 source files that I have on the right-hand side here, you'll notice that the first source file does define that flag, and the second source file does not define that flag. And then I have 2 APIs down here that are receiving this object that I've defined on the left, and I'm calling the same API in both of these source files. So you can see line 14 on both of these files is identical. Okay, now I'm going to go ahead and build and run this in Xcode, and this is today's version of Xcode. You can download this from Apple's website today, and you'll notice that the APIs that end up getting called are 2 completely different APIs. In the example for the one.cpp, it's calling the API that we would expect. But in the second instance, where we don't have the flag defined, it's actually calling the optional API. So this is one of these scenarios where you're looking at your code in runtime going, well, I called the API. Why am I finding myself in the optional API? And you'll notice that when I do the build here, that Xcode is perfectly happy with this build. It gives me no errors. It gives me no warnings. It just builds it and runs it. Absolutely no problem. So what we've done is we've built ORC to actually wrap the linker so that all the libtool and LD phases will go through ORC on their way through going into the linker. And so we can actually enable this. What I've got is this particular build setup is running through ORC, and ORC actually found this issue but is emitting it as a warning. But now I'm going to turn on the warning as error mode in ORC, and I'm going to rerun this project. And you'll see as soon as I do that, I now have an error inside of Xcode, and it tells me that it was unable to link together this project because ORC actually found this ODR violation. Now, don't worry if this text is too small right here. Lee is going to, in a couple slides, go through a breakdown of exactly what this report is telling you. But suffice it to say, this tool will pass over all the sources during the linker phase of the building of your product or the building of your component, and will identify these one definition rule violations and report them to you and prevent the build from proceeding if you so choose until these one definition rule violations are resolved. So I'm going to jump back into PowerPoint now. And I'm going to give it over to Lee. He's going to talk a little bit about the nuts and bolts of how ORC does what it does.
Yes, so ORC ORC is an executable. It is roughly a replacement, or roughly does the same sort of job as the linker. It's going to scan all the object files that contribute to the whatever you're building, library, DLL, executable. And it is going to look at the dwarf information, which is the debug information, the dies for all those object files. You can see how we got to the name ORC out of dwarf. And it's going to verify that for a given object, for a given path to an object, that all the attributes, all the dies for it are identical. And any mismatch, ORC is going to flag correctly as an ODR violation and report it back to you. This is a massive job, and we spent a lot of time on it, and honestly, it was a lot of fun. But we can process 200 million dies, and that's not kidding, 200 million dies and 50,000 compilation units in about a minute. ORC is well optimized. It's a modern C++ multi-threaded program. It is using, right now, it's using upwards of 80 gigabytes on one of our test beds, but the newer versions get that down to about 50 gigabytes, but it uses a lot of memory. And so if you want to run ORC on a big project, this is an opportunity to get your company to buy you a new, better computer. That's what I tell everyone. So, next slide. It takes a lot of inputs. I mean, to set this up, like I said, ORC works much like the linker, so you don't want to just sort of be typing in the command line for ORC. It's a massive command line. So we've done that for you. So it can be inserted into the Xcode build as a pre-linker. The instructions are provided with the ORC build. It's pretty straightforward. And that's going to then do the scan talked about, and it's going to put the output right into the build output as Foster showed you. It's convenient that way. It's reliable for CI. It's sort of how we do the in production in Adobe at Photoshop. But it also does have a standalone mode. Obviously, it's not a super convenient mode to be run in a tooling mode if you're debugging or you're testing or whatever. So it can be run standalone as well, and just copying the command line you want to use. Next slide. So what does an ORC report look like? It's not super friendly, but it does give you the information you need to debug. And so on the left was the example that Foster showed. On the right, ORC is going to, when it finds an object that's mismatched, it's found an ODR violation, it's going to print out a bunch of information. And I've highlighted the two things, or highlighted the one thing in the two locations that you should know, which is the V-table locations for the methods are different. And that's clearly going to cause a problem. But it can find many different things here, and the size and how it's declared, and give you the location and the source files where you can go look at it, debug it, and start resolving those problems. Next slide. Ooh, and I get to hand it back to Foster, and we have a couple minutes. We might want to go a little more. A
little quicker. Okay, yeah. Great.
About the numbers on ORC.
All right, I'll get ripping. So, right, the demonstration example that we gave inside of Xcode, obviously makes for a good demo, but it's very small, and you're probably asking, well, how well does this scale? And as Lee intonated in his slides, we can actually do quite a bit of processing, and we do in the case of Adobe Photoshop. So we have a unit test application that we use to build out Photoshop, specifically the targets that we build for Photoshop on the iPad. And this unit test application shares about 95% of the sources that it has with Photoshop on the desktop. So it's pretty safe to say that whatever issues that we see in the Photoshop unit test application are issues that also exist on the desktop. So a full rebuild of this builds about 82 individual components compiled all from source. They vary in size and complexity quite dramatically, but suffice it to say there are 80 quote unquote smaller components that get built individually. And then there are two large components that get linked at the very end. One we call lib Photoshop, which is that large library that contains most of the Photoshop application. And then the final application that is the unit test framework that we wrap atop lib Photoshop so that we can do our smoke testing and make sure that it's behaving the way we want. So this build takes about 40 minutes on a 2017 iMac Pro. So obviously, if you've got a more modern machine, it'll take less time. But that's a pretty standard build rate for Photoshop these days, especially on older hardware. So here are the numbers that we were able to generate for that unit test application through ORC. You'll see the smaller components that are up top. The median number of translation units is about 23, with a standard deviation of somewhere about 200 and a maximum of about 886 source files. The number of dies that get processed in a single pass over one of those components is anywhere from 77,000 all the way up to 7 million dies in a single component. Most of these components do build cleanly because they don't, they tend to be written by a single group, and so they don't have any ODR violations within themselves, but some of them do. And we definitely am finding some components where there are ODR violations defined within themselves. Where those components start to come together is where things get really interesting. So the large library where we're building out libphotoshop is about 1,800 translation units and 128 million dies getting processed. You'll notice that there are actually no ODR violations getting reported there. And the reason for, and the reason for that, is because, as I mentioned before, the linker assumes that ODR violations don't exist in any components. So when the debugging information gets built for these components, they come up clean. That's why there are no ODR violations in the large library. However, when the final unit test application is brought together and all the components and all the source files are finally linked together, we're looking at about 200 million dies being processed. And this unit test application today clocks in at about 520 ODR violations inside the application itself. So it's definitely a serious issue inside of Photoshop, but suffice it to say, the ORC tool is able to run at the scale of Photoshop and is giving us some very valuable information that we can now use as a metric to drive down to zero. All right, now I'm going to hand it off to Lee, who's going to talk about using and improving ORC.
Yes, and so first off, I'm going to encourage everyone, if you've got an even medium to big code base, take the ORC challenge. And by that, I mean it's open source, pull it down. It's straightforward to build and use. The results can be a little unsettling once you find that you do have ODRVs, but much better to know, much better to track, much better to be able to do something about it. And it's real open source in that we're not just pushing some code that we have at Adobe. We work on it on GitHub. And in fact, Foster and I are going back on working on a couple PRs now. So yeah, I invite you to try it out. Next slide. Another very useful way to use ORC is if you have an ODRV, kind of problems that Foster mentioned earlier, rather than trying to solve those in your debugger, which can be very, very difficult, it's actually often very successful and much easier to just run ORC over it, look through the ORC logs and search for types that you see near crashes. When you see a crash on the stack, just search for that in the ORC log to find the ODRV that might be causing it. That seems a sort of a simple and even trite way to debug, but it's often much, much, much more effective than dragging through ODRVs with your debugger. So it can be a great tool for debugging. Next slide. And finally, like I said, we are open source. Again, I'll put out that github.com Adobe ORC. It's up there right now. And we are using it all the time in Photoshop. We are improving it on GitHub, working on taking its memory footprint down, working on making its output, because it's multi-threaded, some of its output isn't quite stable, so you'll get different numbers in different runs, so we're working on that. It's only in the OS X tool chain right now. We'd love to see it other places. We'd like to report more around ORF and just improve the overall quality of the reporting. So there's lots going on there. And again, invite you to check it out.